Hello everyone, this is Vincent Lin and I'm a senior student in ECE. Today I would like to talk about human pose estimation. So the motivation for this project is to apply human pose estimation in our daily lives. I usually don't go to the gym to work out, but my posture is not correct and caused me some hurt in the back, lower back. I read some paper about using human pose estimation in checking the posture of the athletes to prevent injury and help them to learn correct motion. I think that's very interesting. However, there are some problems with the current models, which is they are not very accurate with video inputs because most of the state-of-the-art models are focusing on the image human pose estimation. So I implemented a paper with the model called DC Pose, which is a state-of-the-art model focusing on video input human pose estimation. The first implementation I did is to reduce the training time because DC Pose was trained on 2 NVIDIA GPU and data set is around 100 gigabytes. So it's very hard to train on my own computer. What I did is I modified the code to let it accept small data set, and also I delete some part of the model to reduce the training complexity. As you can see in the slide, I decreased the number of convolutional network to only 1. After doing this, the training time has significantly decreased. However, the performance also decreased. So in the second implementation, I tried to solve this problem. The DC Pose assign higher weights to the frame that's closer to the current one with the top formula where PCNs are the frame index. For example, if the frame index are 134, the previous frame is far from the current one, so it will be assigned with lower weight. However, this is only useful when we are doing the ablation test because during the training, all of the 3 frames are continuous. So I came up with another formula, which is the bottom one. In the picture, the dancer is moving his arm, and the distance of the arm in the first 2 frames are less than the distance in the next 2 frames. So it's more likely that the current arm will appear near the first one because they're closer. So I use this formula to increase the performance in checking the high movement, the fast movement, and it works. The third implementation is building a classifier to classify the input data with the distance we got from the second implementation. The design of deformable convolutional network with different dilation rate is to capture different movements. For example, the small dilation rate are used to capture subtle movement in the video. However, in the first implementation, I reduced it to only 1, and it's not very accurate in checking different movements. So in this implementation, I tried to add another one with the highest dilation rate and the lowest dilation rate to capture both of the large and small motion. Then I built a classifier to separate the input data into big motion and small motion using the distance data we got from the second implementation. For example, in this picture, the arm in the first 2 frames are moving slowly, so the distance is little, which is then fed into the convolutional network with less dilation rate to capture the subtle movement. In this way, we can train the convolutional network with only 2 dilation rate to capture different movements accurately. So for take-home messages, I think my contribution for this project is I decreased the training time with the lowest cost. By lowest cost, I mean I decreased the dilation rate, because in the ablation test in the paper, it shows that the convolutional network with different dilation rate actually have little effect on the performance. That's why I deleted it. The second contribution is I consider the distance in estimation. I haven't seen any algorithm in the paper I read so far, so I think it's pretty novel. The third implementation is training the model with specific input data. I think this will help us to train our model specifically for different kinds of input. And that's all. Thank you so much for listening.